Today we're going to use partial derivatives. Remember partial derivatives? They work like this. A partial derivative with respect to y treats x as a constant, right? So if you have a function of x, a wild exponential appeared. You use differentiate with respect to x. Take partial with respect to x of e to the x, treating y as a constant. You just get e to the x, right? It's not very effective. Now take partial with respect to y of e to the x. Treats x as a constant, so this is e to the c. Partial derivative is 0. It's super effective. There you go. That's how partial derivatives work. Well, we want to continue and say, what can we use those for today? Here's the first application. In Calculus 1, you talked about tangent lines to a curve, a function of one variable, y equals f of x, I should write here. In multivariate calculus, we're going to talk about what is the equation of the tangent plane. We're going to officially define it later, but we're going to actually start using it today as we talk about differentiability and differentials. So in Calculus 1, we said f of x is differentiable at x if the derivative exists at x. In other words, limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x is 0. Where you're thinking of making a small increment in x to delta x and take the slope of the secant line through those 2 points and then take the limit of the slope of the secant lines. That's what that was. Remember that? Now, how shall we say a function of 2 variables is differentiable? Well, it makes sense like this. If you, this is kind of a klutzy definition. You don't have to memorize this. I just want you to get the idea. This is f at some point x, y, where you go out, maybe I should draw this on here, from x, y to another point, x plus delta x, y plus delta y, make an increment in both of those variables, and if the value of the function up at the new point minus this thing, which is the value at the old point, move over slope times increment. This is the change in y if you move in the x direction, right? Because this is the slope of the tangent line moving in the x direction times the run. Slope times run gives you the rise moving in the x direction, or fall. And then plus the rise in the y direction as you move over delta y in the direction of the tangent line. This is really the tangent plane approximation, as drawn, to the value of the function. It says if the value of the function at the point minus the tangent plane approximation to the point divided by the distance between this point and this point in the xy plane goes to 0 as you get closer and closer, then this tangent plane is really a good approximation to the value of the function as you get closer and closer. So we say f is differentiable. So f is differentiable as a function of 2 variables if the tangent plane is a good approximation to the surface as you get closer and closer to the point of tangency. Alright, so that's the definition of differentiable. You don't have to memorize it, it's a mess, but if the value of f at a nearby point is approximated very well by the value of the tangent plane at the same point, then we'll say it's differentiable. We consequently have this. In Calculus 1, you talked about the local linearization. We said L of x, the local linearization function, is f at x0 plus f prime at x0 times x minus x0. That's the local linearization at some point x0 on the x-axis. What is that? It's nothing more than the tangent line. Alright, because look what happens when you plug in x equals x0. You get 0 here. So you plug in x0 to L of x and you get f of x0. It's got the same y coordinate as f did. What's its slope at x0? Well, you take the derivative of this. This is a constant because you plugged in x0. So the derivative is 0 plus 1 times f prime at x0 plus derivative of a constant is 0. So you take the derivative of L of x. L prime of x is just f prime of x0, right? 0 plus 1 times f prime of x0. So it goes through x0, f of x0 with slope f prime of x0. This function has the same value as f and the same slope of the tangent line, but also, what is this? It's a constant plus a constant times x plus a constant, it's an ax plus b. It's a line. So this is a line with the same slope and the same point x0, y0 as the function. It must be the tangent line, right? So we define that to be the local linearization. It's really just the function, the tangent line function. Similarly over here, this is what we want to call the tangent plane for the following reason. L of x, y equals the function at the point plus the partial derivative at the point times x minus x0 plus the partial derivative at the point times y minus y0. We'll call that the local linearization. It's really the tangent plane function. And here's why. If you plug in x0, y0, this becomes 0 and this falls out. This becomes 0 and this falls out. You get the value of the function at the point. So L of x, y has the same value at x0, y0 as f did. And then you take the partial derivative with respect to x, right? This constant has derivative 0. This doesn't have x in it. And so you get 1 times fx. You get the partial derivative of L with respect to x, the slope of the tangent line in the x direction, is the same as the original function. And if you take partial with respect to y, you get 0 plus 0 times 1 times fy. It has the same slope in the y direction as the original function. So it's got the same slope in this direction, same slope in the y direction, and the same value of the function. That's what we ought to call the tangent plane, right? So it's the linear function, if you figure it out. A constant plus a constant times x plus a constant times y is how that multiplies out. So it's a linear function, ax plus by plus c. This is z equals ax plus by plus c. It's a plane. It's a plane that goes through the point of tangency, has the same partial derivatives as f did in the x and y direction. That must be what we're going to call the tangent plane. So that's the idea. Local linearization is just the tangent plane approximation. And now we can use that to do some interesting things. Here is a function, a polynomial in two variables, x squared y plus y cubed x. Suppose we want to find the local linearization or tangent plane approximation at 1, 2. We need the partial derivative, so we take partial with respect to x of this. Remember how to take partial derivatives with respect to x. You just replace y with c everywhere, and you get 2x times c plus c cubed times 1, right? And then put back c was really y. So that's all partial derivatives are, is treating y as though it was c. And now we want to take the partial derivative at the point 1, 2. You can put straight bar 1, 2 means the same thing. Means plug in 1, 2. So you get 2 times 1 times 2 plus 2 cubed. You get 12. Partial with respect to y. Now you treat x as though it was a constant. Take derivative with respect to y. You get the constant times 1 plus 3y squared times the constant 1, x. And plug in 1, 2 afterwards, take the partial derivative at 1, 2. You get 1 squared plus 3 times 2 squared times 1 is 13. So the slope in the x direction is 12, slope in the y direction is 13. The tangent plane is the value of the function at 1, 2, 10, plus the slope in the x direction 12 times x minus 1, plus slope in the y direction times y minus 2. That's the tangent plane. The function at 1, 2 times the partial derivative at 1, 2 times x minus 1 plus partial derivative with respect to y at 1, 2 times y minus 2. And you multiply that all and group it, you get z equals 12x plus 13y minus 28. That's the equation of the tangent plane. All right. Now we can use the tangent plane or local linearization to estimate f at the nearby point, 0.9, 2.1, right, which is near 1, 2. It should give an approximation when we're nearby. So we just plug in 0.9 for x, right, and 2.1 for y, and we get 10.1 is the approximate value of this polynomial by a tangent plane approximation at the point 0.9, 2.1, near the point of tangency 1, 2. All right, more definitions. I think the notation is harder than anything in here. It's harder than the math. But here's the idea. The differential of a function f of x, y, I should put in there, at x0, y0 is df equals df dx dx plus df dy dy, like this. This is the definition of the differential x, y. any particular point, you take df dx at x0 y0 dx plus df dy at x0 y0 dy. It has to be at the point of tangency. But that's the definition of difference. So it looks like calculus 1. In calculus 1, a function of one variable, you took df dx dx with ordinary derivative. It estimated, this was like the run times the slope, gave you the rise, the estimated change in f. Now, though, you have to take the changes you move in the x direction plus the changes you move in the y direction. So it's df dx dx. This is the slope times the run in the x direction gives you the rise in the x direction. As you move that first increment in the picture, like this, it's the rise or fall in this direction. And then as you move in this direction, this is the run times the slope gives you the rise as you move in the y direction. Sum those two and you get the estimated change in the function df. Alright, it is an estimated value of the change in the function. What is, here's a function sine of x, y. What is df, the differential, at this point pi over 4, 1? Well, df is df dx dx plus df dy dy. So we take the partial of sine x, y. This is x times y. I should fix that. I'm thinking about it. And so, if you have, for partial derivative, sine of k times x, treating y as a k, is k times cosine kx. And then you put back k equals y. Okay, so that's the partial with respect to x dx, plus partial with respect to y is x cosine xy, because now you're treating x as a constant, all times dy. So there's the differential at an arbitrary point xy. For the differential of pi over 4, 1, you just plug in x equals pi over 4 and y equals 1, and you get this. Pi square root 2 over 2 dx plus pi square root 2 over 4 dy is df. It's a number times dx plus a number times dy when you're at the point, in any given fixed point. Now, you can use that to estimate the actual change in the function. Here's the picture. Let me show this at the top. The idea is if you have z equals f of xy, this whole shape here, and at x0, y0, this is the value of the function, this height right here. The increment in the function is f at the new point minus f at the old point. This change, and df is f at the point, is the tangent plane value of z minus the value of f at the old point. And so the change in the tangent plane is this much, the change in the function is this much. As you get real close to the point, delta f, the change in the function, is estimated by df, the change in the height of the tangent plane. Now let's put that back. Let's see, there we go. So let's estimate the change delta f, which is the actual change in the function, by df, the approximating differential. Well, we already calculated up here the differential is square root 2 over 2 times, well, as we go from pi over 4, 1, the point of tangency, to the point when I estimate the function at 3/4 1, right? 3 is close to pi, so these points are close together. What is the estimated change in the function by the differential? Well, it's df, it was this, where dx is the difference in the x coordinates and dy is the difference in the y coordinates. Well, there's no change in the y coordinates, y minus 1, so this is just 0, and you get square root 2 over 2 times 3/4 minus pi over 4 comes out to be minus 0.025 approximately. Indeed, the tangent plane approximation, here, if you calculate the exact change in the function, it will turn out to be approximately equal. All right, now let's try it one more time. This time we'll call it the local linear approximation. The local linear approximation is just another name for the local linearization evaluated at the point. So if I want the local linear approximation to 3.01, 3.98. That means find the local linearization and plug in this number. So if this is the function we want to estimate at 3.01, 3.98 by a tangent plane approximation at 3,4, then we can compare the error and see if it's really good. So the local linearization at 3.01, 3.9, at 3,4 of 3.01, the function at 3.01, 3.98, you take f at 3.34 plus partial with respect to x at 3,4 times the difference in the x coordinates plus partial with respect to y at 3,4 times the difference in the y coordinates. F is square root, and you take the point of tangency, 3,4 squared root of 3 squared plus 4 squared plus, what's partial with respect to x of this? This is x squared plus y squared to the 1/2, so its partial is 1/2 x squared plus y squared to the minus 1/2 times 2x, right? Comes out to be x over square root x squared plus y squared. Partial with respect to y is 1/2 x squared plus y squared to the minus 1/2 times 2y, which is y over square root x squared plus y squared. I said that fast, you rewind it or try it yourself and start the video again. But there we go. F at the point plus partial at the point then is 3 over 3 squared, root 3 squared plus 4 squared, times 0.01, the difference in the x coordinates, plus partial with respect to y was y over square root x squared plus y squared at 3,4, times the difference in the y coordinates. There is the local linearization approximation at this point. We call it the local linear approximation. So we take 5 plus 3 over 5 times 0.01 plus 4 over 5 times minus 0.02. We get 4.99 is the local linear approximation or tangent plane approximation to this function at a really nearby point. It ought to be pretty accurate since it's so nearby. Let's try it. On the calculator, you can calculate square root 3.01 squared plus 3.98 squared. The exact value of this function is 4.99004. The error, we'd say, is the exact minus the approximate. We subtract the two, and this one minus 4.99 gives us 0.00004. Certainly, that's a good approximation that we made with the differential to the with the local linear approximation to the exact value of the function. One more thing people like to talk about is the percent error. Maybe we should mention that. The percent error is the relative error, delta f divided by the value of f at the point, is 0.00004 divided by the value of the function, 4.99004. Percent sign means, times 100%. There's a times 100 in there. Times 100%. Percent sign really means 1/100th, so we're multiplying by 1 here, and we get 8.02 times 10 to the minus 4%. 1/10,000th of a percent error is all. So the actual error is 4 times 10 to the minus 5. The percent error is 8 times 10 to the minus 4% out of the value of the function.